Hello everyone, how are you? This is the 8th lab, and where we will find out the name of the lab is that complex formation titration with EDTA, or we can also call that the complexometric titration with EDTA. Actually, this today's lab we will try to find out the concentration of the calcium ions with the help of the EDTA. But the problem is that the calcium doesn't have any suitable indicator. I believe you know what is an indicator. Indicator is a chemical substance which can give a change of the color or change of the physical state which indicate in the equivalence point, okay, by changing its appearance, color or something else. So till today's lab we actually learned gravimetric titration, we learn conductometric titration, we learn pH metric titration. Today we are going to learn another different type of titration that is called the complexometric titration. Okay, so as I said, the calcium doesn't have any suitable indicator, so that's why we actually use some magnesium. Anyway, in this titration you have to keep in mind some very important points. You can call it the bullet points. So in this titration, actually we use the iriochrome black tea as an indicator. Okay, iriochrome black tea as an indicator, and this iriochrome black tea gives different color when with the magnesium. It gives the color with the magnesium. Okay, when it is it forms the complex with the magnesium, at that time it gives the red color. Okay, and at it gives the red color, but when it comes from the magnesium, when it is in the only iriochrome black tea ions, at that time it gives the blue color. Okay, but it doesn't give any color with the calcium. Iriochrome black tea doesn't give any color with the calcium. So since it doesn't give any color with the calcium, so that's why we need to get a help of some other to detect the amount of the calcium. We have to introduce the magnesium so that we can get the color change. So in this lab actually you should also keep it in mind that calcium EDTA complex is much more stable than the magnesium EDTA, and magnesium EDTA complex is much more stable than the magnesium iriochrome black tea complex. So if calcium EDTA and magnesium EDTA is present, okay, if calcium and magnesium is present and you are going to add EDTA, at that time only calcium EDTA will form first. Okay, when all the calcium will be used up, since it is much more stable, so that's why first calcium EDTA will form. So when all the calcium will be used up, then magnesium EDTA will be start to form. Okay, so same for this magnesium EBTA also. That means after all the magnesium EDTA form the complex, then the rest of the magnesium will start forming the magnesium EBT, iriochrome black tea. So the theory of this actually is quite simple. So I want to discuss first the theory, then I will discuss about the experimental part. So in this theory, first what we need to do, first we will take an unknown solution of calcium. Okay, unknown solution of the calcium salts. Okay, so take 10 ml of the solution of that is actually calcium. Okay, calcium ions. I will discuss it later during the experimental part. So this is a calcium ion, and then 2 ml of pH 10 buffer. What is the reason for adding pH 10 buffer? Because as I said, this color change they give it in the high pH. Okay, so and we are going to also add 0.5 ml of 0.01 molar standard EDTA complex. This is actually a magnesium EDTA complex. As I said before, the calcium doesn't have any good indicator, but magnesium has. So that's why intentionally we are adding magnesium EDTA complex. Okay, so magnesium EDTA complex and iriochrome black tea, 2 to 3 drops of iriochrome black tea indicator. So this indicator we are adding. So in this stage we have in our solution mixture we have calcium. This calcium is from 10 ml of the solution C. Magnesium EDTA, this is from 0.5 mole of standard EDTA complex, that means it is a magnesium EDTA complex, and Eriochrome black tea, it's from 2 to 3 drops of Eriochrome black tea. Clear? So in your conical flux you have these three things. Okay. So now if you are adding EDTA, standard EDTA solution from a burette, okay, if you are adding the standard EDTA solution from a burette or like this, you are adding from the burette, then what will happen? So you have initially you have calcium, magnesium EDTA and EBT. If you have only these, then this magnesium EDTA is less stable than calcium EDTA. So that's why it will automatically form the calcium EDTA, and if there is any calcium EDTA will be formed. If EBT is there, it will form the magnesium EBT also, right? And if there is any calcium, it will remain calcium. So in this stage you have calcium EDTA and magnesium EDTA, right? So it doesn't have any color. This has red in color in the high pH. Okay, and again in this stage if you gonna add EDTA, then what will happen? All of the calcium will form the calcium EDTA, and magnesium will remain as a magnesium EDTA in some stage. And even after coming on this point, okay, if you keep adding the EDTA, then what will happen? That these EDTA already make all of the calcium bonded with the EDTA. So there is no more calcium. So then this EDTA will start bonding with the magnesium. It will kick out this EBT, that means replacement reaction. It will kick this, replace this EBT, and EDTA will be added here. So calcium EDTA and magnesium EDTA. Okay, and this EBT will remain as an Eriochrome black tea will remain as an ions. Okay, as we know, these ions has blue in color and this magnesium EBT has red in color. Okay, it is giving the change of the color. Okay, the red wine red type color. So as you see, so if the color change from red to blue, then you can say that the equivalence point came. Okay, so actually in that equivalence point you have calcium EDTA, magnesium EDTA and Eriochrome black tea indicator. Okay, this magnesium EDTA is nothing but the magnesium EDTA you used at the beginning. Okay, you know from here 0.5 ml of 0.01 molar standard EDTA. Okay, so this magnesium EDTA is exact same as this one what you have initially added. Okay, so this EDTA is actually the EDTA what you have added from your burette. Okay, so if you know the ml of burette, okay, if you know the volume of burette, and if you know the volume of burette, and if you know the concentration of the burette, sorry, concentration of the EDTA, okay, then you know the number of moles of the EDTA, right? If you know the number of mole of EDTA, you can easily know the number of mole of the calcium. Okay, so if you know the number of mole of the calcium and you know that you have taken 10 ml of this unknown solution, so you can easily find out the concentration of the calcium solution. Okay, then you can easily find out the number of mole of the calcium you used. Okay, so if you know both of these, the number of mole of calcium in the unknown solid, in your whole solid. Okay, so this is the actually principle of today's lab. Now I am going to discuss about the experimental portion. Okay, so in the experimental portion, first what will you do? You have to prepare the 0.01 molar standard magnesium sulfate solution. Okay, so first you have to prepare the 0.01 molar standard magnesium. How will you make it? You have to take a volumetric flask, okay, of 100 ml, and you will take 0.3 gram of anhydrous magnesium sulfate and dissolve in 250 ml of water, okay, in a volumetric flask, and make it up to the mark. Okay, so if you put a stirring rod, that's fine, and or you can shake it, it will be dissolved. Okay, then you are gonna make a 0.010 mole of magnesium sulfate solution, anhydrous. Okay, now it is a solution. Then I am actually naming it as an A, solution A. Okay, and solution B, how can you prepare? You can prepare the solution of 0.01 molar EDTA solution from 0.1 mole of EDTA. So you can see the concentration is actually 10 times diluted just. Okay, so how can you make 10? This one will be is made for you. We actually made it for you. So you just need to do the 10 time dilution. Okay, how can you do the dilution? Just take the 10 ml of these. Okay, 10 ml of this EDTA in a 100 ml of beaker, 100 ml of volumetric flask, and make it up to the mark with the deionized water. It's very easy. Okay, so if once you make it 10 times diluted, and we are going to name this as B solution. Okay, so you have A, you have B. Now the thing is that this concentration, we are assuming that it is 0.01 molar solution, but it may be not. Okay, what is the exact concentration of this? You have to find out with the help of this magnesium sulfate. Okay, to do that, you have to run the fast titration. Okay, so fast titration is take 10 ml of the A, 10 ml of A you are going to take, and 1 drop of methyl red. Why we are using methyl red? Because methyl red is an indicator for the acid base titration. Okay, methyl red is an indicator for the acid base titration. So if you add methyl red, then the change of the pH, it will give you the change of the pH. As you know, we have to run this reaction at high pH. Okay, at high pH, because the color change, the magnesium EDTS give the color change at high pH, not at the low pH. So that's why we have to make sure that the pH is very high. Okay, so 1 drop of methyl red and then 6 molar sodium hydroxide till the color yellow. Okay, so we are making it basic, and 5 ml of pH 10 buffer. Again we are adding so much of the pH 10 buffer, because to make sure that the solution is completely basic. Okay, plus 20 ml of deionized water and 4 drops of the iriochrome black tea indicator. Okay, so after this, then what will you do? So in a beaker, you are going to add all of these. Then you set a burette with the EDTA. So this one is B. B will be in the burette, and here is the A. Okay, so titration, this one you are going to put it in the burette, in the beaker, and this you are going to put it in the burette. Okay, then if you titrate, and you have to titrate it, and you will see the color changing from the red to blue. What is the reason of changing that? Is the same principle as I discussed before. That is, so here what you have, you only have the magnesium, you have the A means magnesium sulfate, you only have the magnesium sulfate. Okay, and you have magnesium sulfate, methyl red doesn't give anything here, and you have the EBT. So magnesium sulfate and EBT. So this is actually what? Magnesium EBT, it is actually red in color, right? So when the all of the EBT is replaced by the EDTA from from B, okay, so the color is going to change from red to blue. So that's why the color is going to change from red to blue, and you have to run this titration 3 times. Okay, you have to run this titration 3 times, and I am giving you the data for this. So first titration is 10.1, second titration is 10.20, third titration is 10.00. You will use this data to find out the exact concentration of this one. Okay, Now come to the point. Now you have to prepare the unknown solution. Okay, unknown solution. So in the unknown solution, what will you do? That you are going to get an unknown solution of unknown salt of calcium. So if you have a calcium, okay, you don't know what is it. It can be calcium sulfate, it can be calcium bromide, it can be calcium, whatever it is. Okay, it can be calcium carbonate, calcium whatever. Okay, calcium oxide. So if it is a calcium carbonate or whatever it is, so that's why we want to make it soluble something. We know that calcium chlorides are soluble, so that's why we are going to add. So first we are going to take 0.210 gram of unknown salts. Okay, then we are going to add 3 to 5 ml of the HCl. Why? To convert all of the calcium to the chloride ion, calcium chloride salt, because we know that all calcium chlorides are soluble in water. Okay, so we just converted all the calcium into the HCl, okay, into the chlorine, calcium chloride, and we know that calcium chloride is soluble, and then we put the 30 to 40 ml of deionized water and heat and cool it to the room temperature. So we heat it to make sure that if there is any carbonate, if it is a calcium carbonate, if there is any carbon dioxide, so that it can evaporate from the solution. Okay, and then cool it down to the room temperature. So after that we are going to add 2 drops of the methyl red indicator. Why we are adding 2 drops of methyl red indicator? Same as I said, we will run this reaction at high pH. We will run this reaction at high pH. Okay, high pH. So that's why, because the color change is given by the magnesium at high pH, not at the low pH. So that's why we are going to add the methyl red indicator to see actually the pH is very high. Okay, as methyl red gives yellow color in the basic solution, red color in the acidic solution. So you have added these and red in acidic solution, and add 6 ml of 6 molar sodium hydroxide dropwise. Okay, if you add 6 molar sodium hydroxide dropwise, then what will happen? The pH will definitely go up till the red color discharges, and then transfer to a 250 ml of the volumetric flux and make it up to the mark. So you have taken these and make it into the 250 ml. Then you have taken into these 250 ml. Okay, so from this 250 ml, and you make it up to the mark with the 250 ml. Okay, in this 250 ml you actually have this gram of the calcium, this gram of the calcium salt. Okay, now the second titration. So you are going to take 10 ml of this C, okay, as I discussed, 10 ml of C and 2 ml of pH 10 buffer, and this ml of the standard EDTA, and if you take 2 to 3 drops of the electron black tea indicator solution, then if you titrate this one with the same EDTA of B, then you will get the equivalence point at 8.3. You have to do these things again 3 times, and you will get the equivalence point 8.2, 8.1 and 8.3. okay, so if you do that, then from this calculation, is from this data, you have to find out the concentration of the calcium solution. Okay, you also have to find out the number of moles of the calcium ion you used. Try to understand, here you will get the calcium ion you used. Okay, number of moles of calcium ion, but number of moles of calcium in the unknown solid, how will you get it? Okay, so number of moles of calcium is same as the number of moles for the 10 ml. For the 10 ml, right? The number of moles of calcium you used for these is equivalent to the number of moles of calcium for 10 ml. So what about the you got for this one? Okay, you have to, from there you have to multiply with the 25 or more, 25 to find out the number of moles in 250 ml, right? Number of moles in the 250 ml. So if you get the number of moles in 250 ml and you know the mass, and but this mass is actually a salt, mass from the salt. Okay, so if you know the number of moles of the calcium ion of the unknown, so if you know the if you know this number of moles of the calcium ion just if you multiply with the 25 times, then you will get the number of moles of calcium in the unknown solid. Okay, so for the calculation and experimental part, everything is done. So for the calculation